Then we move on to the next presentation on land subsidence contribution to coastal flooding hazard in Southeast Florida, an update by Mr. Wdowinsky.
Yeah.
Yes, is that more or less?
Yeah.
Okay.
Good afternoon. So today I'll talk about something a little bit different than yesterday. It's about the land subsidence in Southeast Florida. And in this case, the location makes the difference. It's not the amount of subsidence. It's not very high, but the importance is it's very close to sea level, and any millimeter can make a difference. And this is some examples what happens in cities. This is here we see this is Miami Beach when we have a high tide called king tide. So some of the street can get flooded. This is in Fort Lauderdale. You can see what happened to the houses. A lot of them are for sale because people don't want to live in a place that nowadays it may be once or twice a year. In the future, it may be more. So the issue of if coastal flooding become more and more severe. And we can see that what happens in the past, this is a study we published in 2016, that there were more and more flooding events. There were in the past, before 2006, there were maybe once or twice a year, and they were mostly due to rain, or there's a storm surge, the hurricane comes. But after 2006, we have more of these king tide events. So that's what the trend in of the past 30 years. And this is the trend for the next 30 years, and it will get worse because we expect an increase in sea level rise. So the question is, before that, we'll say that Florida is one of the places that is most vulnerable to sea level rise. We can see this is a map showing the different states and how many of the population is actually exposed to sea level rise. That the population live in below 4 feet or 1.3 meters. And if they have energy facilities, so in this elevation, and we can see that in terms of population, Florida is very vulnerable. In terms of facilities, Louisiana is the most vulnerable. But in general, the Florida is very vulnerable for rising sea level. And so when we think about coastal flooding, we need to take into account the rising sea level and potential subsidence. Because what it counts is the relative sea level, and so that's what we need to take into account. And you may have seen this figure before in my keynote presentation. So we use two methods for detecting subsidence. One is the GNSS, is a shallow anchor or deep anchor and on top of the buildings. In this case, we're going to use shallow because we're interested in changes of the surface. And we're using INSAR. And again, over here, what do we measure with INSAR? It works mostly in urban areas, and it's the movement of the building. Now, buildings are connected to the ground by foundation. So it can be, if we see localized subsidence, it means that a building has been moved just independently. If we see sets of buildings, it most likely represent not the independent movement of building, but of an area that include the buildings. So we had, by a project funded by the state of Florida, we had a small network for monitoring subsidence. Now, it's very difficult to find places to put GNSS stations. People don't want them in the backyard, so you have to go to public places. So we looked to places where we could find, we had access, so it's either parks, county parks, or at the campus of the university. And unlike GPS or GNSS stations that we designed for measuring tectonics that we're interested to have to hold the monument deep, that we want to see the ground movement. Here we do it the opposite design, put it in a shallow anchoring to monitor the ground movement. So we have these 4 stations, and we look for places where we can find design, and we got help. This is a standard design of the AirScope or the PBO with the solar panels. So as soon as you install them, they're supposed to operate until something breaks down, but it's pretty resilient. And it's also like this station is in a public place, and a lot of people are going there. And the only vandalism that we found that there was the antenna for the cellular communication was broken, but it still continued to work. So we can actually have an instrument in urban area, even people are working there. So these are the 4 stations, and here's the results after 3 years. By the way, we installed the station just a month before COVID started. We were lucky that we managed to put them. So we have by now 3 years of data. This is a vertical component of the 4 stations. And we see that we have 2 stations with about 2.5 to 3. This is these 2 stations in the public places, and we see the uncertainties are pretty high. Now we can see a very strong seasonal component. This we found in many GNSS observation. This is just the seasonality. The ground is moving due to hydrologic load. And you can see that it's not always in phase, but that's the way it is. And here in these 2, we have not very much here. You can see there is lack of data that instruments stopped working. We had to replace that. But overall, it works pretty well. So this is, it helped to hold it, keep it working for years in order to get more information out of that. But this is initial. The second, we use the INSAR, and we use data, one from the 1990s, the ERS 1 and 2, from 93 to 99. There were 24 acquisition, spatial resolution 20 by 20, and processed with SARscape and Sentinel-1 from 2016 to 21, and higher spatial resolution, and with Squeezer that was the processing. So first, the first data set that we already published that in 2020, and what we found over there that there were the subsidence we found in several places. We can see in yellow. These are the location. Most of them they were in the western part of the city, as we can see over here. And that's where we expected to find subsidence, because that part of the city was built on reclaimed wetlands. There used to be the mangroves, and they replaced by houses. So there were a field, and then houses were built on top of them. So we did expect to see their subsidence. The one surprise place was this location over here, that we found subsidence in the eastern, very localized subsidence in the eastern part of the city. And this is about 2 millimeters per year. And this is this place got famous because that's the location of the Surfside building that collapsed in June 2021. So this is the image of where we saw the subsidence of 2 millimeters per year. Now, when we used, one of the questions people asked was, where was any differential subsidence that may cause some kind of differential movement of the building that initiated the collapse. And when we used just the 1 millimeter per year changes or bar, we didn't see any differential subsidence. But so this is where we don't. But when we look at with 0.5, we do see some component of differential subsidence, that the eastern part of the building is subsiding faster than the eastern part. And when 0.25, it didn't really make much of a difference. So we did see some, but it's pretty small. It's 0.5 differential subsidence. Now, the second data set, the Sentinel-1, for 2016, we can see this is the, we have much denser coverage, and we can see that we see some subsidence over here, but not of where the Surfside building was. This is a hotel that was built in 2016, and it subsides at about rate of 4 millimeter per year. So if we compare the ERS to the Sentinel-1, we can see that in the ERS, we see location of subsidence over here. In the Sentinel-1, we see in different location. So it's not, we don't really see exactly the same location. Though we try to see if there are any of the subsiding places in, that we detect in the ERS-1 can be, we find them in also in the 2016. And we find that in some location, most location, it didn't occur the same location. The subsidence, we don't know if stopped in 1999, but it didn't continue in 2015. Here we see some continuation of subsidence here and here, but not here. So most of the places didn't show the same pattern of subsidence. But some places we do see that there is a subsidence that didn't show up in the ERS dataset, but do show up in the Sentinel dataset, suggesting there is a new subsidence, and usually it's very localized and associated with newer buildings. So this is a change in the pattern of subsidence. So what is the significance of our results? So as I mentioned, the western part of the city, this is a air photo from 1927, showing this is the city of Miami Beach. You can see that there was still a lot of trees and water, and it basically used to be wetlands. This is how it looked in 2017, so 80 years afterwards, or 90 years afterwards. We can see very urban. Still, there is a golf course over here, but overall, it's all full of buildings. So some of these areas that used to be wetlands or with very little housing have changed completely. So we changed, as there is a reclamation of the wetlands. And so what happens is when reclaim, we put soil, there is the process of soil consolidations. Typically, the engineer describe it as with two processes. The first phase is called primary consolidation. What happens is it's a nonlinear rate. It's faster. And it's basically the hypo pressure that respond to the overburden, and the sediments of the soil is actually get rearranged. So we have a nonlinear and fast rate. And after some times, there is more organization of the sediment, but still there is some response to the pressure. And it's a longer terms. It's dominated by rain reorganization. And it can be described as a linear linear process. So what we saw that the GNSS monitoring detected subsidence of 2 to 5 millimeter per year. This is during the 1990s. So the subsidence rate of 2 to 3 millimeter represent in the western part of the city, which was reclaimed, is beside one place, we said in the eastern part of the city of 2 millimeter per year. That represent most likely a secondary consolidation where it collapsed. The Surfside building collapsed. We did find some differential subsidence of about 0.5 millimeter per year. So both of them, since it's been a long time, either 80 years after the reclamation of the land, or 15 years after the house was built in 1980. It reflects secondary soil consolidation. The Sentinel-1 data set from 2016 to 21 didn't detect the subsidence of the Surfside building or the Champlain Tower South. Most of the subsidence in the 1990s didn't continue to the 2016. But we did see some subsidence of the rate of 4 to 5 millimeter per year located next to tall buildings, and this suggests this is a primary consolidation due to the construction of these tall buildings. So this is the end. I just want to thank for the space agencies, the European Space Agency for providing the data, the funding from Florida Office of Insurance Regulation, and NASA helped with the second project, and UNAVCO that helped us to construct and operate the GNHS station. Thank you.
Okay, thank you very much. It's time for questions.
Okay.
No?
Shimon, you cite differential movement of 0.5 millimeter per year. Do you trust the technique at this level?
Yeah, it seems there's a cluster on this side and on the other side. I trust the observations. Yes, I do. No, it's within the uncertainties. I mean, if it was randomly, I wouldn't. But you can see that it's well organized. We can see the cluster. So we can see that it's not like one here, one there. We can see that we have a group over here and a group over here. So the spatial clustering, I think, it suggests that it is something then. Now the question, if we talk to engineers and they say that it's not 0.5 millimeter per year, it's not very significant from their point of view. But this is what we found.
We have another question here.
Hi, Shimon.
Hi.
A question. You showed very nicely in your graph, one of your first graphs, the increase of the number of floods in the area. And now, because of all the events or processes going on in the world, this is not expected to slow down again, I would say. Are you aware of any measures or actions being taken, or are you in contact somehow I was just wondering whether something is going to happen.
So we always look for the Netherlands for how to deal with rising sea level. So the people in Miami Beach and in Southeast Florida, they contact the engineers and planners here from the Netherlands to see if we can actually build seawalls and actually try to prevent that. And one of the problems is that Miami and Miami Beach are built on porous limestone. So seawall will work to some degree to prevent from storms and things like that. But if sea level will rise above that level, it's not because they're going to be in the subsurface. Actually, water will actually penetrate through the subsurface. So a real seawall is not a solution, long-term solution, although they're talking about some walls for protections, but it's not a long-term solution for that.
Okay, then one last question.
There was a program on American television where they interviewed the civil engineering staff and the politicians in Miami Beach, and they demonstrated they were raising roads in some places by 18 inches, so that the first floor of the buildings are now below the level. And the reporter said, well, by the year 2050 or 2100, they would, sea level is going to rise 4 feet over a meter. And the politician said, oh,
Well, so it depends which politicians, because as you know, it's very polarized in the United States. So some politician, there was a period with the previous governor that they weren't supposed to say climate change. So it depends. But at the municipal level, people are very aware of that. And that's why they raise the roads. Now, in other cities, like in Virginia, they're raising some of the houses. But over here depends. So if planning new houses, they demand that they're going to be on higher ground. What you do with the older house is after you raise the road. Originally the design is that the road is below the house level. So if there is a rain, it actually drains from the parcel of the house to the road and then go to wherever, to the drainage system or the stormwater system. Now, when you raise the road above the parcel level, actually the rain goes from the road to the lot. So they have the problem over there. And people cannot get now flood insurance because they cannot show that it comes from below, because it comes from the side. So there is a lot of problems that come with that issue of what you do when you raise, you change the law, the landscape of the city that affect the individual also. So, yeah.
Okay, thank you.
You know?